Welcome, everyone. My name is Jeff Bryan from the Volpe Center, part of USDOT. I'm your host on this Railroad 101 webinar, Signaling Systems. I'd like to introduce Dick Cogswell, engineer with FRA. Dick will be our main presenter.
Greetings, everyone.
I'd also like to introduce Jared Fidzikowski, also of the Volpe Center, who will co-present with us.
Hello.
So, Dick, in this segment of the Railroad 101 webinar series, we're going to be addressing signaling systems.
Yes, that is right. We want to impact to those who are in planning and designing new infrastructure and services some fundamentals regarding railroad signal systems. We will introduce the underlying fail-safe principle, then describe signals as interlockings and blocks, and we will portray the differences between the two systems, route signaling and speed signaling, and we will briefly touch on positive train control.
All right, well, thanks. So before we actually get into the types of signals, there's some real basic principles that folks need to know, and in particular we'll start with the fail-safe principle. So Dick, can you explain that?
I'll try.
Okay.
The fail-safe principle is this: if anything on the electrical loop causes the electricity not to flow, the signal system goes to a danger position. The diagram shows a block, that is, a segment of a railroad in which the rails conduct electrical energy in a loop between the battery and the relay. The rails are the conductor of the energy. You can think of the rails as wires. The rails in each block are isolated from the rails in the adjacent blocks. The insulated joints, shown as yellow rectangles, prevent electric current from flowing between the blocks. Within each block, however, the electric current flows at all times from the battery through the relay and back to the battery. When we talk about track circuits, we are talking about the flow of electrical energy in the loop. Under the fail-safe principle, if there's a break in the flow, no current gets to the relay will change the signals to red.
So if anything causes the electricity not to flow, the signaling system changes to red or stop to prevent trains from entering the block where the break occurred.
Right. The signal system changes because a relay is nothing other than an electromagnet. If electricity flows through the loop, the relay lifts up. Electric energy creates a magnetic field to pull up the armature on the relay and change the light to green. Electrical contacts attached to the armature actually make the signals light up. If the energy ceases to reach the relay, gravity pulls the armature down. The electrical contacts turn the signal to red.
So gravity is integral to the fail-safe system.
Yes, the relays are gravity drop relays.
So why does the signal behind the train always turn to red?
The signal behind the train protects the rear of the train. If a train is in the block, as shown in this diagram, the electricity flows through the train, not the relay. It flows from the rails, through the wheel, across the axle, to the other wheel, and into the rail. This route provides less electrical resistance than the relay does, so the current does not travel through the relay.
And since there's no electrical energy to create a magnetic field to pull up the armature on the relay, gravity brings the armature down and the signal behind the train goes to red. So the concept of resistance, more or less resistance, is important.
Energy will flow through the path of least resistance. Electricity won't travel through the relay when it can more easily travel through the wheels and axles of a train.
So what happens when the train straddles a block?
When the train straddles the insulated joints between blocks, the train acts as an electrical conductor between the track circuits, just as in the last example. The electrical current is diverted through the train, not the relay.
So gravity brings the armature down and the signal behind the train goes red.
If you have an 8,000-foot freight train and 10,000-foot blocks, it is not until the last axle leaves the last block that the signal will change to something other than red. When you have short blocks and a long train, the train can occupy more than 2 or 3 circuits.
And what voltage are the track circuits?
Well, track circuits are relatively low voltages, anywhere from 1.5 to 20 volts. That's why it's not dangerous for a person to touch the rails.
Okay, thanks. So let's talk now about the electric lock on switches and why they've become so popular.
Even today, about 99% of industrial spurs have manually operated switches for entry and exit. In many locations, padlocks are the means of securing the switches, but the electric lock is rapidly replacing the padlock as it provides a much higher level of safety. Jared will give us the background.
A turnout in the country, not a high-speed or passenger-oriented turnout, typically has a padlock to prevent the switch from being thrown. When a train is entering or exiting a spur, the crew member gets out of the train and unlocks the padlock. He or she then manually throws the switch to allow the train to enter or exit the spur. Afterwards, the crew member throws the switch back to its original position and relocks it. What are the problems with the padlock method, Dick?
Well, with a padlock, the number one problem is that there is nothing to prevent trained personnel from throwing a switch that, due to misunderstandings, allows a train, which happens to be passing through at speed, to derail. The second problem is that through vandalism, padlocks can be broken and then anybody can throw the switch. This has happened on occasion with absolutely disastrous results, or near misses, as the case may be.
So the electric lock avoids these potential situations.
Yes. We will show on the next slide the electric lock in conjunction with a timer electrically verifies that the signals have allowed trains in the vicinity to pass through or stop safely. The electric lock prohibits the throwing of the switch until a train that may have already entered the nearest track circuit has either passed through or stopped safely.
All right, so Jared and Dick, could you take us through this, moving on to the main line?
Through the diagram shown, we can simulate the steps to the release of the electric lock to the switch, so the red train can move onto the main line.
The starting condition is this. The blue train is already within the block where the turnout meets the main line. The red train wants to move into the main line. The first step for the trainman on the red train is to open a cabinet near the turnout and turn a lever that electrically connects the 2 main line rails. The electrical connection shunts the main line track circuit in the same way as a train would. The signals react. In addition, a timer is activated to ensure the safe passage through or safe stopping by trains on the main line.
So the blue train is able to pass through.
Until the timer runs out, the timer prohibits throwing the switch.
And who sets the duration? And what is a typical duration?
The signal design engineer sets it to fit the type of trains on the line, their speeds, lengths, braking distance, etc. After running time for typically 5 to 8 minutes, the electric lock on the switch is released.
Then the trainman on the red train walks over to the switch and hand throws it. He or she walks back to the train and moves the train onto the main line.
Okay, thanks. So now we're going to talk about moving off of the main line.
Yes, for moving off of the main line onto an industrial spur, the process is quite similar to what was just described. However, typically an audio frequency overlay is added to the mix. For trains moving off the main line, the AFO can release the electric locks on the switch to the turnout. The AFO essentially overrides the timer.
The AFO detects trains on the main line within a couple hundred feet of the turnout, as an overlay to the normal track circuits in blocks.
The audio frequency is ever present, meaning that it is on all the time. The audio frequency itself is generated by a frequency generator at the site.
So is this right? The audio frequency is attenuated with distance from the turnout. So if our red train is a mile away, the AFO won't detect it, but if it's within a couple hundred feet, it will.
That is correct. When it is detected, the AFO will release the lock on the switch. This overrides the timer only for trains intending to move onto the turnout and which are in the immediate vicinity.
And the reason, I suppose, is that entering the main line is inherently more dangerous.
Right, train speeds on spurs are very low, whereas trains on the main line can be 80, 90, or 100 miles an hour or more. To close the topic of electric locks, for the high-speed passenger main lines, we are dealing with FRA-funded projects. FRA requires electric locks to release the switches at spurs.
So how do hazard detectors play into the fail-safe concept?
Well, we have different kinds of detectors. There are slide detectors, there are flood detectors, there are dragging equipment detectors, and these will basically shunt the rails or break the track circuits.
And like a train on the tracks, the detectors will keep the electricity from traveling through the relay, so gravity brings the armature down and the signals go to stop.
Correct. Slide detectors are fences like the one shown on the slide. They are located in mountainous territory about 20 feet or so from the track. If something is detected, a boulder rolls down the hill, the signal changes to red to prevent trains from entering the slide area. A dragging equipment detector is shown in the upper right photo on the slide. This detector is located between the rails to detect anything dragging or broken from the train itself.
All right, and then one other piece I want to talk about before the signals is just about electricity on the railroad and how the power gets to the signals.
Yes, there is one power source which typically runs along the railroad. For various uses, step-down transformers provide power at the appropriate voltage. The railroad is operating in places where local power is not readily available, which is why they have a power source running along the tracks. Higher voltage power is provided to switches, signals, and such things as snow melters. Lower voltage power is provided to the track circuits as shown in the drawing. Jared will describe this.
The power source enters a signal house, shown as the orange rectangle, that may serve multiple track circuits. The signal house is connected by a cable to the rail in each block. The cable is welded to the side of the rail near the insulated joint between blocks.
So now let's get into the signals themselves. Dick and Jared, what signal information are we about to cover, and how will this information be useful to the grantees in their projects?
Okay, we will cover signals at blocks and signals at interlockings. We will go over the signal aspects, or what the different lights and colors mean.
We'll also describe how speed limits are indicated for both straight and diverging moves, and the discussion will cover differences between speed signaling and route signaling.
It is important for grantees to understand the basics of signaling. Many passenger rail projects, as part of their scope, are replacing 1920-era signaling with modern signal technology. So learning the basics will help people to insert new signal segments in an optimal way. To give an example, a passing track or universal crossover is being inserted in the main line. Ideally, if new interlockings like these are being inserted, they should be located at existing signal sites in order to minimize disruptions to the existing signal system. But if geometry or topography don't permit this, then the signal changes can cascade anywhere from 4 to 6 miles away. The cascading effects need to be much better understood. And general principle here, signals will generally tell the engineer what to do at the next signal, typically 2 miles away.
Also, we want to note that the time required for fabrication and installing signaling systems typically is around 18 to 24 months.
All right, Dick, you mentioned differences in signals and speeds permitted depending on whether the railroad is in the speed signaling or route signaling realm.
Yes, there exist today two fundamentally different approaches to signaling in the United States. Route signaling is typically in the West, predominantly with UP and BNSF. Speed signaling is typically used in the East with CSX, NS, Amtrak, and the commuter railroads in the Northeast. There are certainly some exceptions to these generalizations.
And while we're looking at the U.S. map, could we touch on the dispatch centers? Are control towers still used?
Well, there's a few here and there, but they're very, very few. It is generally centralized. The control centers are shown for the three biggest railroads. Each control thousands of miles of track.
And I see UP's center in Omaha, BNSF's control center in Fort Worth, Texas, and CSX center in Jacksonville, Florida.
Yes. NS, CN, CP typically do not have centralized system-wide control centers, but more regionally based centers.
All right, let's move on to talk about signals at blocks, or automatic block signals, ABS.
As we have described, between interlocking is a framework of blocks. Each block is roughly 2 miles long, with actual block lengths based on the worst-case braking train in the corridor. Each block has an independent track circuit that, through a gravity relay, activates changes in the signal system. ABS signals are automatic, meaning they operate without human intervention, and in fact, they cannot be changed by field personnel or dispatchers from a control center.
ABS is designed to be a fail-safe system. As we just discussed, any number of warning devices can cause the electricity in an individual track circuit not to flow through the relay. A break in the rail, a lightning strike, a fuse that breaks, a piece of dragging equipment, and yes, even a train. And all of these will cause the signal behind the event to change red.
In the diagram above, something in Block A has broken the flow of electricity in Block A. The red signal appears between Block A and B, with a downstream yellow between B and C. At this point, the train's personnel focus on the events down the track, perhaps a half mile to a mile away.
All right, so I have a question. The train engineer sees a block signal ahead that is normally green but is now yellow, like in the diagram shown. Does the train engineer slow down and just wait?
When a train engineer sees a yellow, he or she would typically apply the brakes. If the yellow is unanticipated, then they would call the dispatcher to ask about the situation. The dispatcher could respond that there is no train ahead and to slow down and crawl forward to see what is causing the signal to change. Or he could say you are following train XYZ and wait until the signal changes.
And is it typical that the train engineer is the first to become aware of a signal change within a block?
To answer that question about who becomes aware of what and when, this depends on the sophistication of the dispatching control center. When something anomalous happens, ideally the dispatcher control system would display a red light on the control board in a particular block. An alarm would also be transmitted to the dispatcher in some way. But all too frequently, this is not the way it is. Some control centers, the dispatcher only gets information at junctions and passing tracks, but not at each block. This is why when a train is out in the countryside, the dispatcher may only know the train is somewhere between two interlockings, which may be 10 to 15 to 20 miles apart.
Well, let's talk for a minute about the signal aspects. On this slide, we see a single-headed signal.
Yes, ABS signals typically have one head and one lit light. Distance signals, however, typically have two heads, as we will see on the next slide. Before we move on, it is important to note the definition of signals. In automatic block signals, a red signal typically means stop, and you are then authorized to proceed but not exceeding restricted speed, which is defined as 20 miles an hour and being prepared to stop within 1/2 your range of vision. Depending on whether one is in the route signaling or speed signaling world, there are some variations in signal aspects and their meanings. Distance signals provide trains with advance warning of an interlocking, and the home signals are at the interlocking. On this slide, the westbound train moves towards the distance signal that indicates approach diverge. This means continue ahead and diverge at the turnout ahead.
For the distance signals, the top head indicates the straight ahead move and the bottom head indicates the diverging move?
This is typical, yes.
So just to be clear, the distance signal is an ABS signal.
That is correct. The distance signal is part of the automatic block signal system. The distance signal is the last automatic signal before the home signal at the interlocking.
And on the previous slide, we noted that there can be variations in the meanings of the signal aspects. We said that red in ABS means stop and proceed at the restricted speed. Does the red signal at the interlocking home signal mean something different?
Yes, it does. A red signal at a home signal means stop and do not move. Stop and stay.
Well, let's move on to talk about the electrical functions that create the automatic signal.
Okay, briefly, there is a very simple logic sequence hardwired into each signal. This basic logic means that when you have a red or a stop and proceed behind train B, the downstream signal is yellow. For train A, this means approach and expect the next signal to be at a stop.
But how does the information actually feed down the track?
Well, there are a number of variations around the U.S. All signaling systems transmit messages down the track or by means of line-side wire of a coded system, typically a pulsing system. We'll leave it to that for now.
So let's talk about the merits of signal and bidirectional signals.
Signal track railroads have always had bidirectional signals to safely provide for operation in either direction. With double track, triple track, or more tracks in the old days, signals would typically be installed in one direction only, as shown on the slide. Trains going the other direction would have to fall back on manual train order systems. Today, on a double track railroad, the first step to increase its capacity is to install bidirectional signals if they are not already there. At each insulated joint between blocks in both directions on both tracks, there will be a signal.
So we've discussed braking distances in our first webinar, train types and performance, how the train types have different braking characteristics, and we discussed the different braking systems. In the track configuration webinar, we showed how the braking distances dictate block lengths and passing track lengths, and then, of course, signal spacing. So let's talk now about how the braking distances are actually calculated.
Okay, as we have said, braking distances for freight trains are significantly greater than for passenger trains going the same speed. On level track, the braking distance for a 110-mile-an-hour passenger train is roughly the same as for a 60-mile-an-hour freight train. Braking distances are calculated for the worst case condition. For example, an ice storm in February. Following the Code of Federal Regulations, Amtrak and the railroads provide the braking distance information. Jared will go through the factors.
Every railroad has mathematical equations to calculate the braking distance. The calculation starts with an average train on level track. The equation considers grade changes for the topography of the corridor, the weight of the train, the maximum speed of the train, and the braking systems themselves, including whether the brakes on a particular train are not performing optimally. Finally, it also includes weather conditions.
Note that only conventional air and electro-pneumatic brakes can be factored in. Dynamic brakes cannot be used in the calculations because they presume a functioning locomotive. Since locomotives have been known to fail, dynamic brakes are not considered a fail-safe system. The margins of safety are included mean that the real-world braking distances are shorter than those calculated distances for the signal systems.
All right, let's move on to talk about signals at interlockings. And an interlocking is a standalone dispatcher-controlled element. And now we're going to talk about the remote control of interlockings in more depth.
We have stressed that the railroad is a totally controlled environment. I would like to take a minute here to elaborate. The dispatcher clears the route for his train from one interlocking to the next interlocking. While we say that all moves are controlled and the dispatcher sets the route, please understand that the dispatcher cannot change the aspect of any signal. The field logic will prevail. Automatic block signals are automatic, and for interlockings, all the dispatcher can do is request that the home signals be cleared. The term home signal means the entire array of signals at the interlocking. Home signals are normally at red or stop.
Here's the sequence. The dispatcher identifies the route. If the route is a turnout, the dispatcher throws the switch, then requests the home signals be cleared. If the route is straight through the interlocking, he or she requests the home signals be cleared. The dispatcher requests that the signals be cleared only when a movement through the interlocking is imminent. The dispatcher tries to have the signals cleared about 4 to 5 minutes before the train gets to the interlocking.
The dispatcher will typically touch or use a cursor on a screen the entry and exit points of the interlocking and sends the request. The signal logic in the central instrument house actually clears the signals based on the aspect of signals at adjoining blocks. The dispatcher gets an indication on the control board that the signal has been cleared. At that point, the route is aligned and locked, meaning the route cannot be changed and a conflicting route cannot be created. The home signals will change to the best possible aspect, and this signal change will cascade back into the automatic block signal system. If there is something irregular in the field and the dispatcher does not get a clear signal, he may have to radio the train engineer to look at the rails in the vicinity or get the nearest signal maintainer to go over. The problem is typically right at the interlocking.
Is there usually a lot of communication between dispatchers and train engineers?
The verbal communication between the dispatcher and train engineers should be minimal, only when something is out of the ordinary. The dispatcher, especially in operationally dense areas, may have as many as 40 trains under his control at any one time.
What if the dispatcher makes a mistake or changes his or her mind about the route?
Okay, this is why we don't clear signals until just before a train is due to arrive, because there is a time delay associated with making a correction. The dispatcher cancels a home signal and they revert to red, which means stop. A 5 to 8 minute timer is activated to accommodate safe passage through or stopping of existing trains already on the route. This is similar to the use of a timer discussed earlier for trains moving onto the main line via an electric lock. After the time has expired, the dispatcher then is free to set another route. The bottom line is the dispatcher has to run time before revising the route. And again, this may be 5 to 8 minutes out on the main line.
All right, so now let's discuss how the dispatcher actually sets the route for a train.
Dispatchers have two ways of setting routes at their disposal. They are the unit lever and the entrance-exit NX. With the unit lever, the dispatcher sets a specific turnout. The unit lever is used in everyday train movements and is also for track maintenance, for example, to gain access to oil switch points. It is also useful to triage track problems. With the unit lever, the clearing of signals is a separate action from the throwing of the switch.
The entrance-exit or NX method is useful in complex interlockings. With NX, the dispatcher uses a cursor to point to the entering and exiting point. The NX system does all the unit lever operations automatically, including clearing the signal. Note that in the complex interlocking shown on the bottom of the slide, the home signals are the entire array of signals shown above. So you've actually got 8 home signals on that 4-track universal interlocking.
All right, so as we previously said, route signaling is used in the western part of the U.S. Let's talk about the signal aspects in route signaling.
The signals at interlockings typically have 2 heads. The top head for a straight-through move and the bottom for diverging moves.
For example, the first signal aspect on the slide, green-red, means straight ahead, clear. There are many more than the ones shown in the slide, but we just wanted to give you examples.
Okay, bear in mind these signals only tell the train whether to go straight or to diverge. They don't indicate the allowed speed. On the next slide, we will see how speed limits are conveyed in route signaling systems. For route signaling, speed limits are indicated in the employee's timetable for both straight and diverging routes.
An excerpt from Union Pacific's Roseville area timetable is shown. At the right is the scale for elevation change. Across the bottom are the milepost numbers. At Altamont, east of San Francisco, there is an 800-foot grade change between mileposts 50 and 60. This table lists speed limits for straight-ahead moves for the distance between mileposts 50 to 60 for both passenger and freight trains. This table lists speed limits for diverging moves. You can see the speed for the Altamont turnout is 15 miles per hour.
The diverging moves shown here are rather simple. The complex interlockings on the next slide will show some limitations of the route signaling system.
So this example is of a 4-track universal crossover. It's a complex interlocking which there's multiple turnout sizes can be used.
In route signaling, while turnout sizes in an interlocking may vary, only one speed for the interlocking is given in the employee's timetable. That speed is dictated by the lowest numbered or size turnout in the interlocking. So if you have a number 10 turnout, the speed of the whole interlocking is limited to 15 miles an hour.
So why is only one speed given?
Well, as you know, for an interlocking, the dispatcher controls the switching and therefore the track that the train will take. The train engineer obviously anticipates the route, but not the exact track that will be used where and when he is running.
So only one speed limit is indicated in the employee's timetable for each interlocking because there's no simple way in the timetable to provide the speed limits for all the turnout possibilities?
That's essentially correct. And so in route signaling, it is a waste of money to install turnouts that are longer than the lowest numbered turnouts. There is no speed to be gained unless you expect to come back later and change the smaller turnouts to higher turnouts. The Eastern railroads moved away from route signaling for this reason for over a century. And the fact that the train engineer has to constantly refer to the employee's timetable for speed limits for all moves. And it has happened that the train engineer forgets exactly where he is and reads the timetable incorrectly. This can be disastrous. Speed signaling improved upon these things, as we will explain now.
So, Dick, how did speed signaling improve on those limitations?
Well, for moves through interlockings, the signal aspects themselves convey the speed limits for that particular move. This is a huge improvement because it means that a mix of turnout sizes can be used. The turnout sizes are commensurate with their use. In some areas on the East Coast, the railroad network is highly complex with over 600 trains per day, 4 to 6 main line tracks with crossovers and branch lines heading everywhere. In situations like this, speed signaling is essential. With speed signaling, signal aspects exist for each turnout. When the dispatcher, who has full control of the route, remotely throws the switch, the train engineer reads the speed limit for the selected turnout or crossover.
In speed signaling, there are 3 heads. One light is lighted in each head. All 3 lights are read as a total message. So for example, on the far left, we see green, red, red. That means clear. Go track speed.
With any green, the train can go ahead. Whether the green is in the top, middle, or bottom head tells the train how fast it can go through the interlocking. Green in the middle head typically means 30 miles an hour. Green on the bottom head means only 15 miles an hour. Flashing green is less restrictive than a solid green. Why? It is electrically fail-safe. That is, if the flasher fails, the light would become a solid green, which permits a lesser speed.
This slide shows sample speed signal aspects. This isn't all of them, but it'll give you a good idea of how they work.
And keep in mind, stop always means stop and stay. Do not move.
So a question for you, Dick. The first aspect, green, red, red, means go through the interlocking at track speed and continue. So how are track speeds indicated?
Well, unfortunately, we still go back to the employee's timetable. The train engineer refers to the employee's timetable for the track speed going straight through the interlocking. The speed for diverging moves is found in the signal aspects. In speed signaling, different turnout sizes within an interlocking can be used safely, allowing for generally faster speeds. On the slide, we see a large 4-track universal interlocking that uses a combination of number 24 turnouts, number 20s, a number 15, a number 10 for an industrial area.
And I understand that because the turnouts are so long and so heavy, that 2 switch machines are needed for a number 20 turnout, and more switch machines may be required for a 24 turnout and larger.
That is correct. Some of the very high-speed crossovers, turnouts, may use as many as 5 switch machines. A complex interlocking like the one shown above will have a large number of switch machines, and since these switch machines, a number of them may be operating at the same time, the power requirements can be significant.
Dick, we've talked a lot about the fail-safe principle and how it's manifested in railroad electrical, braking, signal, and communication systems. Given all this, why have we had the number of accidents recently?
Well, despite the fail-safe equipment system, trained personnel can still exceed speed limits. They can advance through red signals at interlockings, even as supposed to stop, and they can fail to stop and proceed at restricted speed at an ABS red signal. This is why Congress, through the Railroad Safety Improvement Act of 2008, mandated that positive train control be implemented across a significant portion of the nation's rail industry by December 31, 2015. Positive train control is required essentially on most Class 1 mainline railroads, roughly 70,000 route miles of track in the U.S. Positive train control enforces the speed of the train. With PTC in the route signaling world, the train engineer will no longer depend entirely for speed information from the employee's timetable. The signal system in the cab will tell the engineer to slow down to X many miles per hour. And if the train does not slow down, the positive train control system on the train will slow it down automatically. PTC requires a lot of computer programming. For each segment, it factors in the topography, the size of the turnout, train weight, braking efficiency, curve sizes, etc.
Okay, well, this wraps up the signaling system webinar. So, again, Dick, what would you say are the main messages that people should remember?
Well, certainly train braking distances essentially set the spacing of signals. To run trains without signal restrictions, the spacing between consecutive trains is set by the worst-case braking train. Remember the cascading effect of signal changes to the existing signal systems. Positive train control will display the speed limits in the cab and will enforce all speed limits, both signal-induced and civil restrictions.
Well, that's it for the Railroad 101 webinars. We hope you've enjoyed the series. To see this or any of the webinars, see FRA's website, Rail Network Development /Oversight Guidance at the fra.dot.gov website. Thank you, Dick and Jared, and all of you.